Thank you for coming, and I'm excited today to talk to you about our work on using Canary inputs to dynamically steer approximation. My name is Michael Laurenzano, and my co-authors on this work are Parker Hill, Rezat Samadi, Scott Malky, Jason Mars, and Ling Jiateng, and we're from the University of Michigan. In many cases, we can get by with less accuracy. This is really one of the ideas that underpins approximate computing, which is that in many cases it's desirable to trade small losses in accuracy for large improvements in either performance or energy. What really got us interested in this problem and why we started looking at it is that we observed that there are a number of application domains such as machine learning, data mining, image, video, and sound processing, statistics, and graphics, where there's loose constraints on the quality of output along with large and growing computational demands via applications like intelligent web services, intelligent personal assistants, wearable devices like watches and glasses that have image and sound inputs. It's really the confluence of these things, having loose constraints on quality of output, along with large computational demands, that really makes these applications ideal candidates for approximate computing. So we're thinking about building approximate computing runtime systems. Really one of the central questions we have to answer is how do we approximate? So we can sort of decompose this into two parts. The first is how do we parameterize approximation? In many approximate computing techniques yield parameters. These are knobs that can be turned up and down to trade different amounts of accuracy for different amounts of performance. If we think, for example, about an image processing approximation technique called tiling, the fundamental idea is that you want to compute one pixel exactly, and you project the results of that pixel onto the surrounding pixels to create monochrome tiles. And this approximation technique can be made more aggressive by making the size of the tiles larger, and it can be made less aggressive, getting less performance improvement but more accuracy by making the size of the tiles smaller. So really one of the goals of approximate computing runtime systems is deciding how do we parameterize approximation? How aggressive do we make it? Secondly, we need to answer where in the application do we approximate? It can be the case that we have many different code regions, many loops, functions, etc., that are amenable to approximation, and the job of the runtime system is to decide which of those, if any, to approximate, how to parameterize approximation within all of those code regions. Really, one of the cases I make in this work, and the insight driving this work, is the insight that input really is and should be a key component in terms of answering this question as to how to approximate applications. To sort of drive this home, I'm going to go through an example where we think about a gamma correction application. This is an image processing application where the idea is that you want to adjust the brightness of the image to make it more consumable, more easier for humans to pick out detail within the image. So if we think about a couple of inputs to a gamma correction, we have these two inputs. We have a bird on the left and a flower on the right. And here we can look at exact outputs. We run an exact gamma correction on both of these inputs, and we have these brightness adjusted versions that are outputs. On the left, we have this brighter version of the bird, and on the right, we have this brighter version of the flower. In the case of the flower, you can actually see some more detail in the background of the flower, really kind of underscoring the point of what gamma correction is all about. If we think for a second about how these two inputs behave, if we apply a particularly parameterized approximation, this is an 8x8 tiling approximation. So we have an identical application, we have an identical approximation technique, but we have different inputs. We can really see here is that the quality of the outputs that we get here are significantly different. In the case of the bird, the approximate output looks very similar to the exact output. In the case of the flower, there are some pretty substantial differences between the approximate output and the exact output. And so it's really, this sort of underscores the fact that there can be wild differences between the quality of output that we see across different inputs, even with the same application and even with the same approximation technique. So if we study this idea a little more thoroughly, we can go through an example where we take this gamma correction application in the context of two different tiling approximations on a span of 800 different inputs. So, excuse me. What I show here are two graphs, each where we apply one of the tiling approximation technique, one of the tiling approximation parameterizations across all these 800 inputs, and we characterize what's the output quality that we get across those 800 inputs. These are histograms of the output quality that's achieved among the different inputs. So the taller bars mean there are more inputs where we see a certain level of output quality. Really the key point that I want to drive home here is that there's a large span of different levels of quality that we get, even if we're applying the same approximation technique. And it depends significantly on the characteristics of the input. In the 4x2 tiling case, we see that the output quality ranges between 91% and 99+%. So really And so if we imagine that we had a runtime, if we imagine that we had a system that allowed us to take full advantage of the differences among inputs, what would it look like? What we have here is, or what I do here is an experiment where I take this gamma correction, I take these 800 inputs, and I run a large space of different approximations on them. For each input, I choose the approximation parameterization that's fast, that yields above 90% output quality and is the fastest approximation to do so. So as we can see on the left here that we have sort of by construction, we meet, if we imagine that we have this 90%, we have a 90% output quality represented by the vertical dotted lines in these graphs. We can see that sort of by construction we have above 90% output quality. It's an oracle. Really the interesting fact here is that what we see here on the right is that we get a 61 speedup on average, and there's a wide range of speedups that we see depending on what the properties of the input are and how we chose to approximate given the characteristics of the input. And so it's really this idea that animates this work, is that we want to get from a place where we're instead of applying a single approximation technique across a large number of inputs, we're really customizing how approximation works on an input by input basis. And so we have this goal of achieving input responsiveness. And so to be more concrete, the goal here is to build an end-to-end runtime system that allows us to choose how to approximate in a way that's customized for each input. So the goal is, what we're trying to do here is maximize the performance we get out of approximation given a particular accuracy target. There are a couple of challenges that we encounter when trying to build such a system. First of all, we need to be able to choose a highly effective approximation. It's an approximation that delivers a large amount of speedup while still delivering sufficient levels of accuracy. And the real challenge, and of course we can imagine ways of doing that. There are many conventional approaches based on doing things like computing exact results and comparing various approximations to those in order to choose how to approximate. Really fundamentally, these kinds of approaches are untenable because they take too much time. And the idea behind approximate computing is that we want to really improve the performance of our software, and so really the goal here should be to choose how to approximate very quickly. And so embodying this idea is the system we've built called input responsive approximation, or IRA. So we step back for a second and think about an exact model of execution. What we have here we have a full input. It goes to the exact program. Some processing happens, and out the other side comes an exact solution. This is running the program, running without any approximation whatsoever. If we think about what I'm going to do now is talk about how IRA works in the context of 3 specific steps that we have to take, that the system takes in order to derive an approximate solution to the full input. So at the outset of the problem, we start by creating this Canary input. It's a small version of the full input that we're going to use to dynamically characterize the behavior of the full input in the context of a number of different approximation parameterizations. So what we're going to do is running runtime experiments that allow us to discover how to approximate the full input. We're going to do it with this small Canary input to allow us to do it cheaply. And the fact that the Canary input is small is really a reflection of the fact that in many application domains, the computational complexity is driven by the size of the input. And so the fact that the Canary is small really allows us to make these choices, run these experiments and make these choices in a very computationally inexpensive way. So sort of in pictorial form, the way this works is we take the full input, there's some set of steps that happen, and out the other side comes this Canary input. It's this small version of the full input. Once we have this Canary input, we want to choose an approximation using the Canary. So we have the Canary input, we have some target output quality, this is an accuracy constraint that we want to satisfy, and we have some space of possible approximation options. The goal here is to choose the right approximation, an effective approximation for the Canary input to derive this customized approximation method that's fast and high quality on the Canary. Once we have this customized approximation solution for this customized approximation method for the Canary, we take it and we compute an approximate solution on the full input to derive a final approximate solution to the entire problem. So that's sort of an overview of how the end-to-end system works. So let's get into a little bit more detail about some of these components. So this whole system is driven by this idea of canaries. So what are our goals in creating these canary inputs? So first of all, we're going to be using the canaries as a model of the execution behavior of the full input. So first and foremost, we want the canary to be sufficiently similar to the full input. It's not much use to us as an execution model if it doesn't behave similarly to the full input. So that's priority number 1. Secondly, with the backdrop of approximate computing, really the goal is to improve performance. If we spend a lot of time creating the canary, it eats into the performance and it eats into the speedups that we can achieve, and so it really undermines the purpose. It really directly undermines the purpose of approximate computing. So really, it's important that we be able to create the canaries very quickly. We also want to reduce the size. We want to have the size of the canary be as small as possible as well. As I mentioned before, the computational complexity of many types of applications depends on the input size. And so in order to keep these runtime experiments, these dynamic experiments cheap, we want the canary to be as small as possible. Okay, so how does this canary creation process really work? So we have, what I show here is a full input. In this case, it's an image. I'm going to go through the entire example using images as the sort of motivating example. We can also apply these same ideas to other types of data structures, be they one-dimensional arrays, multi-dimensional arrays, or arrays of structs, and so forth. So we start with this full input, and we create what we call a batch of canary candidates. These are regularly strided subsets of the full input. That are in the case of images, we can think of these as smaller versions of the input image. We take all these canary candidates and we compute the similarity between each of the canaries and the full input. So there's a number of ways we can think about what it means for two inputs to be similar to one another. In this work, we explore 4 different definitions of similarity, ranging from simple things like mean and variance, where, for example, when we're looking at we want to make sure that the mean of the values in the canary input is similar to the mean of the values in the full input, to more sophisticated and complex metrics like local homogeneity and autocorrelation, where we're ensuring that sort of small-scale local features that exist in the input or in the canary input are similar to the full input. And so, of course, because one of our goals was to perform this computation inexpensively, the approach we take using this is a statistical one rather than performing exhaustive computation to do all these similarity comparisons. And so because we're using statistics, one of the inputs to our system is a set of error bounds. This is the willingness we are to accept the possibility of making mistakes in computing these various statistics. And so it's also worth noting that inside that similarity comparison box, I'm sort of hiding a large amount of detail in terms of a large number of equations and statistical machinery and statistical challenges that we had to overcome to get this whole thing to work. So we're using a hypothesis testing framework when we're comparing canaries to the full input. Because we're using multiple canaries, we run into something called the multiple comparisons problem. And there's all kinds. There's 2 types of errors you can make in statistics. There's type 1 and type 2 errors. So we have to address all of these things. And I'll point you to the paper if you want to get any more detail about any of these specific issues. Okay, so the purpose of this similarity computation is to derive a set of canaries that are deemed to be acceptably similar to the full input. So what comes out the other side of this box is a set of canaries that are deemed to be similar enough to the full input. And this sort of helps us meet our goal of making sure that the canaries are similar to the full input and really will represent the full input's runtime behavior in a loyal way. Once we have these acceptably similar canary candidates, we choose the smallest one to result in a canary input that we're going to use as the object of our dynamic search. And of course, the fact that we choose the smallest one, given that they're all acceptably similar, we want to choose the smallest one so that the search that we're going to do next, or the choosing how to approximate, is as inexpensive as possible. So now that we have this canary input in hand, really the goal is to take it and use it to choose how to approximate. How do we want to approximate the full application? So the goal here is to tune the approximation parameters within all the code regions of the application. The approach we take to doing this is to use a greedy search algorithm called steepest descent hill climb. So let me explain a little bit about how this search algorithm actually works. So this is a search that's driven by this canary input. What we're going to be doing is running differently parameterized approximations on the canary input and plotting them in this speed up versus error space. Also part of this space is this vertical line labeled TOQ. This is an accuracy constraint that we want to meet as we're approximating the application. Also, I want to point out that the labels on the points here, rather than being points in this space, are actually the encoding of the approximation parameters that are being tuned by the runtime system. In this case, because the vector has length 2, there's 2 code regions, 2 parameters that need to be set by the runtime system. Okay, so the way this search starts is that we begin by computing the exact result on the Canary. This, by definition, has no error and no speed up. We take that and we incrementally turn up each of the individual approximation parameters, and we see how they fit into this speed up versus error space. So we can see here that we have the points 1, 2, and 2, 1. In this case, the point 1, 2 yields the steepest ascent in this space. So we're going to use that point as the starting point for the next iteration of this search. So we start with 1, 2, we go down to 2, 2, and 1, 3, and we can see here that both of these particular parameterizations yield too much error. And so this actually halts our search. We go back to the last known good parameterization, and we use this point 1, 2 as the final approximation. And it's this final approximation that we're going to apply to the full input to get a final approximate result for the entire application. Okay, so now that we have an idea of how the whole system works, let's turn to evaluating and see how well that actually works. So before I get into the meat of the evaluation, I want to describe some of the details of the experimental setup. We use 13 applications drawn from the domains of machine learning, data mining, image and graphics processing. Within each application, there's between 1 and 5 approximation opportunities. There's between 1 and 5 parameters or code regions that need to be, we need to parameterize the approximations among them. For each application, we have between 2 and 800 inputs, and we're going to run IRA on the application across all of these inputs. We apply 4 different classes of approximation techniques among these 13 applications. In some cases, they're mixed together within the application. These approximation classes are loop perforation, tiling, algorithm choice, and numerical approximation. It's not really important to understand the details of how these techniques themselves work. Really, the key to understand is that they all have these knobs, these parameters that need to be set, and choosing how aggressively to approximate. It's the job of the IRA runtime system to set those knobs. Throughout the evaluation, I'm going to be using variance as the Canary similarity metric. There's a lot of detail in the paper just exploring the issue of how these different similarity metrics work. It turns out that across all of the metrics, we actually get very good accuracy properties, but the simpler metrics tend to result in smaller canaries and still very still very useful and informative canaries. But it's the simpler metrics that result in smaller canaries and those faster searches, and so it's this variance metric that results in the largest speed up overall, and so that's the metric we use throughout the evaluation here. We also use a target output quality, an accuracy constraint of 90%. Meaning we want the runtime system, the goal of the runtime system is to deliver an accuracy of 90% relative to exact execution according to a particular application-specific error metric. Okay, so I'm going to start by looking at comparing IRA to a class of prior work called calibration. This is sort of the state of the art in terms of choosing how to approximate. The idea behind calibration is that you want to occasionally compute an exact result on the full input and compare that exact result to approximate results in order to gauge whether your approximation is too aggressive or too conservative. And really, the underlying idea behind calibration is that you can only use it occasionally because it's so expensive to do. It's very expensive to choose how to approximate across every input using this technique, so you have to use it very sparingly. So ultimately, calibration techniques end up applying one approximation parameterization across a number of inputs. The specific approximation, the specific comparison that I'm making here is against Oracle versions of a system called Sage, which is published at Micro 2013, and Green, which was published at PLDI 2010. So the graph I'm showing here has each of the applications along the x-axis, and the height of the bar represents the speed up that's achieved running the approximate application with IRA versus exact execution. So higher bars are better here. And so, I meant to mention that the particular comparison I'm making here is these Oracle versions of Sage and Green, where there are various parameters various settings that need to be set in terms of how often to calibrate, how to change calibration as the system is running, as it sees more inputs, and it's those parameters that these are Oracles because those parameters are set by Oracle for each application. So really the key takeaway here is that IRA gets a 10x speed up across all these applications on average, and outperforms Oracle calibration techniques by a factor of 4x. And so this really highlights and the cause of this is that IRA is customizing the approximation per input, but Oracle calibration isn't. So how does IRA do on delivering on this target output? How does it do on delivering on this accuracy constraint? So what I'm plotting here is the percentage of outputs, for each application, the percentage of outputs meeting the target output quality. And this is, of course, a target output quality of 90%. So in most cases, IRA meets the target output quality in 100% of the outputs. There's a few cases where it's 90%, or sorry, where it's in the 90s of percent, and in the lowest case, it's actually 94%. But on average, we meet the target output quality in 99.4% of cases, rather. And so it does a good job of meeting this target output quality constraint and delivers enough accuracy in general. So next, I want to look at where the time is spent. In the end-to-end execution of IRA, where do we spend most of the runtime? So here, what I'm doing is I'm showing you the execution time of the IRA system broken down as a percentage of the runtime that you get running the application exactly. And so the yellow portion of the graph here represents execution time saved by running the application approximately, rather than running the application exactly. The other three colors are the other three colors. We have the green, where this represents the time spent creating the canary. You almost can't see it in most cases. You can sort of see it in the Gaussian filter application. We have the time spent taking the canary and using it to employ this search algorithm to choose how to approximate. That's the blue. And then finally, we have once we've chosen that approximation technique, we apply to the full input. That's the red part. So really, the takeaway here is that choosing how to approximate, which is the green plus the blue, it turns out to be very fast and not a particularly onerous process in terms of, and it actually is done very quickly. And so IRA does a good job of meeting that goal. Finally, I want to look at how IRA does in terms of delivering on input responsiveness. Does it actually approximate differently across different inputs, and do we actually achieve different speedups? Do we aggressively approximate when we can? And so what I'm showing here is for each application, the speedup that we get, the speedup that IRA gets versus exact execution as a distribution across all the different inputs that we have for the application. And so really the takeaway here is that there's often a wide range of speedups that are possible across the different inputs, depending on the characteristics of the input. What we see here is that IRA is able to conservatively approximate when that's what's needed, and aggressively approximate when it can. And so it really does a good job of squeezing lots of performance out of the cases that it can. So finally, to conclude, one of the things I showed that IRA is and should be really a key component in approximation. We took that idea and we built an end-to-end runtime system called IRA. This IRA system is driven by these canaries, these small representations of full inputs that will serve as models of execution for the full inputs. So quantitatively, we achieve a 10x speed up across applications at a 90% target output quality, and which outperforms dynamic or Oracle calibration techniques by a factor of 4x. With that, I can take questions.
Hi, thank you. That was a very nice talk. Can you go back to the slide where you have the time breakdown, the time you spend creating canaries and everything?
Yes.
So I'm very impressed by the fact that the canary takes so little time to create. If I just take the 2D image processing like Gaussian filter, let's say I have an image of 1 megabyte. How many points of the original image do you have to read in order to compute your canary? Is it like 10% of the image you sample, 1%?
Right. So one of the details of the system that I didn't actually get into is that you tend to want to keep canaries that are significant. You want to limit the canaries to canaries that are significantly smaller than the full input, because as you're using it in this dynamic search, if it's say half the size of the full input, things are just going to be there's going to be too much runtime overhead. It'll be too expensive. So what we limit it to is canaries that are at least 1/16 or smaller of the full input. So you end up touching small fractions of the input in most cases.
Okay.
Does that answer?
Yeah, I just get it.
Thank you.
Hi, I'm Dan Barry from UMass Amherst. I didn't quite understand the quality of service constraints. So can you explain, this is something like an annotation that the programmer has put in, or the user or something, right?
Yeah. So this paper is not tackling specifically how to annotate the program and things. There's a number of nice works that's kind of come from this community in terms of expressing these types of constraints programmatically. And so the assumption is only that there is some constraint. It's specified somehow by the programmer, and the system takes that into account when deciding how to.
Okay, so could you use something like signal to noise ratio? Would that be an acceptable constraint?
Yes, of course, of course. So the system is pretty much agnostic to the error metric. You call a function, you plug it into this, to the runtime system, and it does its thing.
And then just one other question.
Yep.
The Lucas cannot thing. So I noticed that was the one like negative result on the other page, where it did not outperform the sort of the basic thing. So what's the insight? Like why did that one not do well?
Right. So why does Lucas cannot not do well? So it turns out that Lucas cannot actually be approximated. There's one parameterization that works well across all the inputs that we could find, and so in that case, where there's sort of constancy in terms of how you can approximate, there's minimal additional value from this type of system. Thanks. Hi, Catherine.
Hi. Nice talk.
Thanks.
So I want to follow up on the question the first person asked. So when you want to create a small canary, but to do the statistical test that you have a representative canary, you have to, how much more of the data do you read? Do you read the whole array to compute those statistics?
No, we do not. So we're using part of the calculations that we're making are you compute a particular number of samples that are needed to achieve a particular statistical power in terms of getting enough samples, in other words, to make the right statistical comparison.
So how do you compare the statistics for the canary with the full input? How do you reduce, so you're further reducing the full input when you're sampling to make that comparison?
Yeah, so your statistic, you're randomly sampling from the full input, and you're randomly sampling from the canary with a particular number of samples that's computed automatically by the system.
All right, thank you.
We got more.
On the canaries. So since it's like so cheap to create canaries, I don't see like why don't you create like 1 million canaries and try to get to one and maybe get even better performance. Maybe you can talk more about that. It's very interesting.
So the fact that it's so cheap to create probably has to do with the fact that we're not creating 1 million of them. So if you created 1 million of them, it might be, the green part might be quite a bit larger. And so discovering exactly what the limit of that is an interesting question. But it's often the case that, for example, for an image, if you have say a 1K by 1K image, in terms of putting together, regularly strided subsets of that, think of, you can have an image that's a fourth the size, an eighth the size, a fourth, a 16th, and so forth. There's only so many of those that you have access to, right? So the smallest one being a 1 by 1 pixel canary. Right?
So other than sizing, was there something else, or is it just sizing?
This is largely driven. Our system is largely driven by size. We found that to be a sort of particularly important property as it pertains to keeping a loyal representation of what's going on in the full input.
Okay, thank you very much.
Sure. Hi.
Hi, John Gold from UMass. Do you find that the found parameters differ significantly across inputs, or is there often 1 or 2 sets of parameters that seem to work well across inputs for particular domains?
I think if I understand your question, are you asking, are there parameters that are useless? Is that the question?
No, so you mentioned that for Lucas Canary, the one negative example, that there's one particular set of parameters that work well for almost everything. Is that true across the other domains? Do you think that you would be able to save time if you reused parameters that were on different inputs?
So in general, it's the case that there are a large set of different parameters that are chosen by the system, and if you're sort of thinking in terms of optimality, you do want a large space of possible parameters. You can certainly imagine, improving both you can imagine improving, say, the search time for the canary. You can reduce the size of that search space significantly by doing things like pruning the search space via profiling or some other tech or static analysis or something. And so you can certainly imagine, cases where where such things are useful, like Lucas Canada would be one such case. I think in general, most of the search space turns out to be pretty useful.
Thank you.
Yep.